Well, hello, we're back in the basement lab here, and we have on test the same antenna we had in the last video. That's this little antenna here. This antenna is a quarter wave vertical at 869 megahertz, and it's the antenna that comes inside these Harvard Engineering WiMAC remote control street lighting devices. And these are the devices you see on top of the street light, certainly in some areas where they're using them. And the idea of it is it enables remote control of street lighting, so that the local authority can potentially dim lights in one area if it's not busy, turn them on or off depending on activity in that area, whether or not the lighting is needed. So rather than all the lights going on at dusk and going off at dawn, they can be controlled with a bit more granularity. And the idea, of course, is to save electricity and reduce your carbon footprint. So these devices are on top of lampposts, and we tested this in the last video and saw that it is a low gain vertical antenna. In fact, it has less gain than my little dipole I made here out of an old Wi-Fi aerial and bits of tats, and this has about 1 dB gain more than that antenna. And of course we tested it against an actual high gain antenna, which is this homemade cantenna here, which is of course high gain. This is high gain because the energy which comes from the little antenna inside is radiated out this way because it's reflected off the back and the sides of the antenna. So it's basically like a TV antenna. You have a TV antenna, it's directional, and you point that antenna towards your local radio TV station that you want to receive. If it's omnidirectional, it's a bit like a donut, like putting this bit of tape on here, and you can see that it will transmit and receive equally in all directions, whereas a TV antenna, or the antenna that I have here, the cantenna, will transmit receive better in one direction than another direction, and that is called the forward gain of the antenna. So what we want to do is find out whether or not this antenna is directional. Does it transmit a better signal in one direction than another direction? So we have the same setup we had last time. I have a Lime SDR, and it's transmitting a carrier wave on 869 megahertz exactly. And we have another software-defined radio receiver just down the hall there. You see it just down there. It's inside that door there, across the side of the basement, and that's receiving the signal from here. And what I've done as well is set up a little stand to put the zoom out, to put the antenna on here, and it's just got some direction on it. It says north, northeast, east, southeast, south, southwest, west, northwest. And what I'll do is I will turn it around. So currently it's facing 0 degrees north. I'll turn it then to northeast, east, etc. around the points of the compass at 45-degree intervals, and we'll see in what direction, if any, this antenna has more gain. I suspect it'll be very, very little in it, or maybe a tiny bit, maybe sort of half a dB or so. But let's find out. So let's start the test now. We have the antenna here. It's pointing currently 0 degrees. There we are. And we're transmitting, and the antenna is oriented so that the side of the antenna with the printed track on is facing 0 degrees. There we are. So 0 degrees is now facing towards the receive antenna. Let's have a look at our receive signal. It is it's about neg 45 degrees or so. Decibels rather. Neg 45 decibels. Let's now turn the antenna around, being careful to make sure that we're spinning the antenna around this axis here. So if I just put my finger there and try and keep it there, we'll now move it so it's going to be pointing northeast, say 45 degrees, about there. And our C signal is now 45.2, 45.3-ish. Let's now move it around so it's at 90 degrees. Again, hopefully keeping that antenna in the middle. And 90 degrees. There wasn't it? Oh, it looks like it's changed a little bit. So neg 43.5, so about half a dB in it or so. It's moving around a bit. Let's now move it round to southeast. That's 135 degrees. Ooh, get my finger on there. There we are. Pointing southeast, we have a received signal strength of neg 44.2, 0.3ish, still roughly the same. And going around the compass again, let's point it north, northeast, east, southeast. Let's point it south now. So now the printed track on the antenna is facing that way. And our received signal is neg 45. You've gone down a tiny bit. There we are. Okay, let's now move it around the compass again, and now we're going to go south, southwest. Let's move southwest. Antenna cable's getting a bit wound up there. There we are. Southwest is there. And look at the receive signal. It's neg 44.8.9. Again, very, very little at negative 45. There we are. So round now, we're going to go to west. I'll flip that cable over. There we are. It's pointing west. Lay that cable flat. Doesn't cause too much trouble there. Okay. Let's flatten that properly. Okay, there we are. And what do we have now? We have what's neg 45.5, 0.4ish. There's a tiny bit in there. I wonder what's causing that. Let's have a look, shall we? Let's see if we can find out why that is slightly higher there. Probably to do with the antenna cable orientation. So move that around there a bit. There you are. So I've moved the antenna cable a little bit, and we're pretty much back to where we were, aren't we there? Neg 43 point something, edging up to neg 44. Okay, so let's now move it round to northwest. So again, we try and keep our point exactly the same. So it's going to point northwest now. There we are. Just a little bit there. There we are. Okay. So look, what do we have now? We have neg 43.8, edging up to neg 44ish. Maybe half a dB in it or so. And finally, we're going to point it back north again, back to where we were. And let's have a look. We're back on, yeah, neg 43.7, neg 43 point something, so edging up just towards neg 44. So what we found is that this antenna, notwithstanding the fact that moving the antenna cable around will cause a tiny fluctuation in the signal strength, it is pretty much across those 8 points of the compass, it is equal gain. There are some people saying that perhaps there is a higher gain on one side, on maybe the side that, a bit of dodgy camera work there, maybe on the side that has the printed antenna track, or maybe there's a higher gain there than there is on the reverse side, but no, it's pretty much exactly the same gain, whatever way you point it. Let's do a little experiment now, see what happens if we point it end on towards the receiver. So that's going to be, how do I do that? That like that. There we are. Let's have a look. So end on towards the receiver, we have a lower signal. So it's quite sort of, what, 6 dB lower, neg 53-ish. There it is. End on like that. So there we are. It is an omnidirectional antenna. It transmits and receives with equal strength in all 360 degrees radius arc around the center point of the antenna, with sort of plus or minus half a dB or so. How do we explain that plus or minus half a dB? Well, the antenna is a ground plane antenna, and ideally on a ground plane antenna, the ground would be equal in all directions around here, but it isn't. There's a slightly larger ground here and slightly shorter here. And we also have the antenna cable here, which will affect the radiation pattern slightly. So that will account for sort of 0.3 to 0.5 dB difference we've seen in some directions of the antenna here. But all in all, it is pretty much a typical omnidirectional antenna that you'd expect to find. Why is it omnidirectional? Because it's on a lamppost, and you don't want the engineers, when they go and fit these, to have to mess around with aerials, making sure they point to the right space station. So we just put an omni on, and also it's absolutely fine. It works perfectly well for this this kind of use case. You don't need high gain antennas. It's a very low power network. The receiver is very sensitive, so there's just no need for it whatsoever, and it makes the installation, of course, much easier because there's no antenna alignment that has to be undertaken. So, I mean, that pretty much concludes it, really. I mean, what we could do, I suppose, is let's see if we can make it directional, maybe by adding a parabolic reflector behind it, and see if that can increase the received signal strength. Let's try that, shall we? So, I couldn't find some silver foil or tin foil or anything, so what I've done is found this piece of old microwave. This is just like the lid off a microwave. That I'm taking to bits. There we are, and I'm going to use this as a corner reflector. So what will happen is that this corner here of the microwave lid will act as a reflector for the antenna. It won't quite stay on there if I stick it on there, so what I'll have to do is to point the antenna, rather the camera, towards the screen so you can see that, and then I will hold this up manually so we can try and get the reflector pointing the right way and see if we get a higher signal strength. Remember, of course, that the lower the number here, the lower the negative number, the higher the received signal strength. So if it goes from, what do we have now? We have that neg 45-ish. If it goes from neg 45, we see it increasing, then we know that we have a stronger received signal at the receiver. So here we are. I've got the piece of old microwave now, and I'll hold it by the antenna without cutting myself on it. Put it back there. What do we have there? Oh, neg 41. So right away we have what's it? Neg 41.5. There we are, and that is neg 44. So there we are. Right away we have 3 dB gain just by sticking a bit of old microwave behind it. So I can get that a bit better, shall we? Just right. Move around a bit. It's not the best because there's bits of microwave all over it. Let's see if I can bend it out of shape a bit more. There we are. And try and keep away from it so it doesn't affect the signal. Oh, there, neg 42, neg 41. I'm just moving the microwave case around a bit now. Try and get the right direction. There we are. So that's pretty good. So just by sticking a bit of old microwave behind the antenna, basically just like this there, just holding it behind the antenna here, and the result is, of course, that on the antenna you have the antenna there, and there's a corner reflector. So the signal from the antenna will radiate towards the front, as it always will do, but the signal on the back here will start to reflect off in this general direction. It isn't very good. It's not a massively high gain bodge, But it just demonstrates that this antenna on its own is not a high gain antenna because it's literally a piece of wire on a circuit board. This is just a gold-plated copper track there, and all it does is radiate the signal equally in all these directions. Which is why when you put a reflector on the back, because some of the signal is radiated behind us, behind the antenna rather, then it will be reflected back from the reflector off to our receiver, resulting in a higher signal strength at the receiver. So there we are. This antenna is not only not high gain, it is also not directional. It is in fact omnidirectional. It transmits, receives equally in all 360 degrees around the antenna. And not much more to say really. It's a dead simple antenna. It is, as I think I mentioned on the last video, equivalent of a ground plane antenna, which I've lost now. Oh, it's on my receiver, that's why I can't find it. It's the same as a bit of wire and some metal at the bottom. That's all it is. So there we are.